And today we'll finish up assembly. Typically in previous semester, we have 3 parts to assembly. This time I spent a little bit more time with the explanation, and we want to kind of wrap up how function call is done before I go into the topic that I personally like. One of the topic that I'm really comfortable with it because my thesis involved around designing this thing. Memory hierarchy, how to design a way to serve the data to the CPU. What happens when you need the data, like when you have an array or when you access DRAM, what actually happened? Um, so if you are curious about the memory technology, memory hierarchy, how to access data, exactly, I really, really want to tell you the cool things that we've done to make data access really fast. All right. But it's also really, really important in computer system. You need to know how this works because otherwise the computer will not function the way you know it. It's going to be really slow. All right. So for that, let's do a quick recap, right? On Tuesday, we talk about the jump table, and the way it works is you have the switch case, right, that have a bunch of code block. Each code block would be corresponding to the case inside the switch case statement in C. The way it works is basically it's a big assembly. All right, you would use a technique called indirect jump. So the first jump will be a jump to this table. The first will be a jump to this table, which contain many pointers, if you will. Basically, it's like another jump to the actual code that you need to go to, depending on the value of the input to the switch case statement, right? And we go with this example where you have a switch case in C right here that convert to the jump table, and we expand into how does the jump work. So now I can ask this on the exam if I want to, and hopefully you should be able to answer. And then the in-class exercise that we plan to cover today, we'll actually talk about the jump table as well. But on top of it, we'll talk about how the function call works, right? But before we go to the function call, there's a way that x86 and many processors actually manage the memory. And the way they manage this particular area in DRAM is done in the stack discipline. What does stack discipline mean? Basically, this works like a normal stack that you see in life, right? When you stack things on top of each other, you can only remove the top part. You can't just go in the middle and remove something because the stack would collapse, right? So that's what the stack discipline. You can add things to the top and you can remove things from the top, right? And in x86 stack, right, there's a special register called the stack pointer that always point to the top item. And whenever you insert a new thing to it, this pointer, this register would move to that new top item, right? And this is a region of memory. It's actually something exists on your DRAM that x86 manage along with your OS. Windows, Linux, and Mac OS would manage this in order to handle function call. Because again, when you look at your code, right, when you write code in C, in Python, in Java, every single language, right, when you look at it, how many function call do you see? Can someone tell me how many function call you actually write in your homework or on your exercise? Function calls. Well, okay, you can have just the main function, but there's one function call too, right? And in a real program that let's say you run a startup company and you want to launch some product, right? For example, you might be the guy who write. How many people use while grind so far to test for memory leaks? While grind, quite a few of you actually, right? These are program. You can write the program similar to while grind, right? That works to check the bug on your code, right? That you can write a program to debug a program. GDB is actually a program used to debug your program, right? So in this kind of production level program, imagine how many function calls you have to do to manage many things, right? And this is one example alone, but think about it. Let's say you have a web application running on the server and also on your client, right? When you go access certain website, right? Some code would run on your machine, some code would be run on the server. There gotta be so many function calls involved, right? How many people imagine then how does the computer manage all these function calls? Right? Because at the end of the day, everything comes down to assembly, right? So let's say I have this function, mouse store, that call mouse2, which is this function. It's basically a function that call another function once to do the multiply. The second function return the result of the multiplication, and the earlier function just return that value in the pointer. That's it, right? This is a really simple program. The first function do nothing except for calling the second function, which multiply two numbers together, return, and that's it, right? But because we have function call, and similar to any program, basically, right? You need to manage how am I going to keep track of where things are. Because let's go back to this concept real quick. How does your computer know the exact line is running right now? I need to run a program. So I need to be able to tell at any given time, right? What line in my program am I running? So how can I do that? How can I do that? Through the program counter, right? Let me go a little bit deeper by using a correct terminology. This is actually that's an execution model, right? Where you basically how does the program work? How does it run? Does it run line by line by line by line by line? In C, like at least in C, does it run like line by line? From line number 1 to line number 2 to line number 3 to line number 4, except for a few cases, right? Where you have if else or for loop, right? Well, most of the time, the way you update the program counter is what? You go to the next line, right? You go to the next line, you go to the next line, you go to the next line. For example, if you're here, right? You then go to here, and then you go to here, except for a few cases where if you're here, you call a function, then you jump here, right? But this model is actually called von Neumann. The reason why I want to bring it up is I want to actually bring up the word. The definition of this model is called von Neumann. And one important thing about the von Neumann model, von Neumann is actually a person. He is a computer scientist, and he's one of the forefather of the computer as we know it, as we use it, right? And von Neumann model, one of the thing in von Neumann is you run a program line by line. You have line number 1, followed by line number 2, followed by line number 3. So what's the benefit of that? Can someone tell me what's the benefit of that? What would be the benefit of the von Neumann model? It's easy to read and write too, right? As a programmer, it's also really easy to write a program. So for those of you who are taking FunPower right now, can you raise your hands? FunPower folks? FunPower folks? How does it feel writing program in functional language? Compared to Python, which is crying. Yeah, so you realize, right, that the complexity to program go up. Because I mean, to be honest, the way we think about many things, you would like as a human, we finish one task at a time. And when tasks are sequential, right, life is simple. I finish task 1, followed by task 2, followed by task 3, right? And that's just the simplicity provided by von Neumann, right? But if you start programming by looking at functional programming, then you can prefer the other style because it's close to a math function. And yes, it's actually really clean, right? it's actually really clean. So if you once you get how these things are done, it's actually really nice too. And the benefit, the other model is different. These are called functional language, and the way you execute the code is called data flow model. Data flow model is basically whenever I have all the inputs to my function available, I'm going to run it right away. It doesn't have to be done in the order as I see from the code I write, right? And that's a data flow model. So the benefit of that is, why do you learn fun part? Why do you learn Rust? So what's the key benefit of Rust? Save code for sure, yes. What else? Are you guys on the, it's fast. It's fast. And are you guys on the parallelism yet? Yes, parallelism. Yeah, you can then write a program to run in parallel really easily. Right? So that's why there's multiple ways you can invent a program and also the language to the program, right? And yes, Rust complains with, yeah. So I was about to make jokes. It's kind of like me. I complain a lot. I complain all the time, right? But at the end of the day, it's just for performance, right? And to make sure things are safe. But at the end of the day, when it goes to assembly, how do you keep track of the line you are? I mean, to be honest, some of you already answered that on the chat, which is awesome, right? Through the program counter, the program counter actually tell what line are you on. Now I'm gonna go sidetrack a little bit. These things I'm gonna say next is actually not on your exam. All right, not on your exam. But how many people know that your CPU also, even though you write a code line by line by line, your CPU try to run it as if this is a functional program because it's faster. It actually doesn't run line by line by line. It's opportunistically take whatever line it can run so that your CPU can run really, really, really fast. It doesn't run one line at a time. It can run 4 or 5 or 6 lines at a time, depending on the specification of your CPU. Actually, these days things are really complicated. If you want to know more, right? If you want to know more, definitely let me know. There's already a few people interested in the special topic, computer architecture. So if there's enough people, I am more than willing to open the class and share with you how to design a chip, how to design a computer chip, and what are the key things in there. But anyway, so let's just come back to this concept. I have function call, right? So if I say I can track what line am I on through the program counter. So what happened here? So what happened here when I call another function? What would happen to the program counter? What should I do? How can I jump to another function? What would happen to the program counter? First of all, you push the program counter to the stack. Why do you have to do that? Because you have to save where you are, which is this line, so that when you finish the call, you can jump back to the function that call it, right? At the correct line as well. So that's the first thing. You push the program counter to the stack. Then what would happen to the value of the program counter? What would happen to the value of the program counter? You change the value, right? You change the value from the program counter to be this line, right? And then that's how you manage the program counter. So this is basically PC is program counter. So program counter management, right? You can use the stack to keep track of what function call what and at what line. So when you have like we call this procedure call, these are function call, right? You push the return address onto the stack. Then you jump to the new location. Then when you return, right? when you return, you pop the address because now you have the program counter on a stack. If you pop it back, you know what line you have to go back to, and that's all, right? And here are the example, right? When you call the function, right, the stack pointer will increment because, well, it should be decremented because stack pointer go down. It grows downward. So to get decremented, the program counter would point to the next line here, right? 400550. Then you save the old program counter in the stack so that when you finish the function call, these save program counter would tell you that, hey, okay, just go back here, right? When you return, you pop, and then you can now go back to the original function. And that's all. That's the only thing you have to do. If you have this assumption, can I now call recursive function? We are all familiar with recursion, right? The function call itself many times. Are we all familiar with recursion? Should be. That's an example code to Fibonacci through recursion. Remember our Fibonacci using recursion? It's one of the sample code I did earlier. So if I have this assumption, now can I maintain all the function call if I want to implement Fibonacci through recursion? Yes, no? Anyone? How many people think now I'm good? I can just keep track of the program counter on the stack and then I'm good. Now, how many people think there's something more I have to do in terms of keeping track of what function call what? What's your thought on this? Come on, let's think a little bit. Is this enough? Is this assumption enough? I just push the program counter on the stack. I jump to the function that I need to jump to, and when I return, I just pop it back. Is that enough? Okay, how about this? How many people think that seems enough? And that should be it. Can you raise your hand if you think that seems enough? Well, so how do you put the condition to stop if I have a recursion? Who is responsible for that? Is it the hardware? Is it the language, or is that the programmer? Who is the one responsible to tell when to stop for a recursive function? The programmer, right? The programmer needs to basically put the correct algorithm in. So it's not the job of the hardware. It's not the job of the compiler. It's not the job of the ISA or the assembly code, right? So then is that enough to handle all things function call related? If I have this particular assumption that whenever I call a function, I push the program counter on the stack, and when I return, yeah, right? It actually is enough. That's it. That's the only thing you have to do. And then you can call as many functions as you want, and you'll be good. Your program would work, right? This is actually why I tell many people that when you look at how to design the hardware and how to design the system, simpler is usually better. You want things to be simple. In this case, it's really simple. Just one assumption. Make sure everything works accordingly, right? And it's beautiful, actually. It's just the only thing you have to do, push things on the stack, and that's it. All right, so now we handle function call. That's it, actually, really. We handle the part where we know where to jump back, where to jump forward. What else am I missing? What else am I missing? So let's say I have fib of 5, right? I handle where to go in terms of the function call. Have I handle what to do if I need to pass data in and pass data out? Have I done that? Have I done that? No, right? I haven't talked about it. So let's talk about it. Function calls pass in the data and return certain data out as well, right? So let's do this first really, really easy thing. Return value. How do I return something? So what has been our assumption so far? What has been our assumption so far about the return value? Yes, just put this on %RAX. That's it. If you want to return something, when you are about to finish the function call, make sure that's in RAX, and that's all. Why is that okay? Why is that okay? If I have this assumption that everything I want to return will be in RAX. So let's say you have function 1, right? That call function 2. I will call this function 1 a caller, and this is a callee. As long as I know that the return value will be in RAX, is the caller good enough? Like, will I then know how can I find the return value? How can I find the return value? Is that good enough? As long as I have the assumption that once the function call finished, the return value would be stored in RAX. Is that good enough? Right. Basically, then your assumption will make the color job simple. I look at RX and that's my return value, right? Great question. This is a great question. What if the register is not large enough to store the return value? So how big is RAX? How big is RAX? 8 bytes. How big is the biggest data type that I can have in C? Like a singleton data type, like double float and int and all those things. How big is that? So how long is long? Actually, let's Google that. All right, so depending on the architecture, most of the time it's either 64 bytes, 64 bits or 32 bits. Is that more than 8 bytes? Is that more than 8 bytes? No, right? So is my register enough to store that return value? It's enough, right? So at the end of the day, in that case, generally it's enough. But let's say I need to return some weird struct or something. In that case, it's the job of the compiler to figure out how to return it. Most of the time, the key things is put that in the memory and make sure you know where is that in the memory. Because memory is bigger than a register, right? As long as you can return the address, you know where they are, so you can identify that piece of data. Exactly. You can then store the address, right? Oh, long double is 10 bytes. Okay, I didn't know that. So that requires some trick on what do I do with RAX and what do I do with how do I return it. So then you combine multiple instructions together to know that, okay, if it's long double, the caller now have to be aware that where's my data. All right. So is it more clear now? Basically, it's a series of assumptions made by both the caller and the callee. And these things are in your control when you implement these things in assembly because you are the programmer. Right? Is your control. The ISA are the tools, and you as a programmer, you program things. So as long as you have the same assumption for the caller and the callee, you're good. All right, now we covered the return part. Can I do the same trick with the inputs? Because function can take multiple inputs, right? So can I assume that certain register would have the first input, another register would have the second input? Can I do that? Is it? You think so? And I think so too. So let's do that, right? So to pass the data in, right now the modern architecture, right? The first 6 arguments, how many of your function calls having more than 6 input? How many of the function call would have more than 6 inputs? Not a lot, right? Most of your function call would be at most 6 inputs into it, right? This would be your first input, second input, third, fourth, fifth, and the sixth input. Anything more than that, put it on the stack. So just push, 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 right? Is it clear? These are the assumptions made by the program. Your first input will be in RDI, second input will be in RSI, third input will be in RDX, fourth input will be in RCX, the fifth input will be in R8, and the sixth input would be in R9. And the return value, once you're done, will be in RAX. In the meantime, you can then use this register. As long as when the function call happens, you put the correct things in these register, you're fine. All right, any questions? Why is this good? Why is this good? Where is the stack? So let's do some discussion, right, on why is this a good design. Where is what's the location of your stack? Is it on a CPU or is it in DRAM? So let me go with where's the register? Is that in the CPU? When you buy a CPU like Core i9, does it come with the register? Yes, right? These are in the CPU for sure. Where's your stack? Is it with your CPU or is it something that the OS built inside DRAM, inside the memory? Where is the stack? Is the stack, the actual location of the stack is actually in the memory. We will not talk about the cache yet. Yeah, in the RAM, basically. These are in the RAM. We will talk about the cache soon. The cache would try to make the memory access a lot faster. But let's save this topic toward the second half of the class because that's a big topic, right? The stack is in the memory. Which one is this slow? Which one of them are fast? Register is really fast. So to get to the register, it's probably take usually these days with your modern CPU, maybe around 2.3 nanosecond to get to the data in the register. For the memory, it would take 12 to 50 or more nanosecond to get to your memory. So is it a good idea to put the input into the register rather than just push it on the stack? Is that a good idea? It is, right? Because it's actually faster. So now let's go through some example. Let's say I have this same function mount store, right? Oh, okay, great question, actually. What kind of measurement tools can time this? Um, there's multiple tools that involve like things like circuit design. So you can go all the way to circuit simulator like Spice. Actually, let me open it up for you. So so this is a copy from a handout from Stanford, right? This is a really common tool that you can we typically use it for like a college level circuit simulation. It's called H-Spice. I'm not sure if there's an image here. Nope. So let me find some image. Sorry about that. Here, right? So you can put like multiple circuits together and you can then run it. It would give you the measurement for your circuitry. And this is actually one of the really common tools that you can use to measure how fast is your circuit. Because at the end of the day, everything you do inside the computer, these are electronic circuits. So you can time them. You can time them. And if you can time them, you can simulate this. Then there's also another set of art and science that goes into how do I build this simulator. Then you build an actual device. You build an actual device and then you measure all these things many times until you have the model. And once you have the model, you can plug that model into this simulator. All right. So is it more clear? Is it more clear on how do you like get these number? All right. So that's one thing. For the memory, right? The like, so I'm gonna show. I'm not sure if I have this. Give me a second. I want to show you the actual picture of it here. Got it. All right, so I'm gonna show you a slide. I'm gonna steal this from Yugo Kim, my good friend. Is currently at Google. So this is his thesis defense slide, and he's one of the guy that we were working in a lab in my devices group at CMU, and he is one of the guy who do a lot of work in main memory, and he had this thing. We have this thing built. Where's that slide? I can't locate it. Why can't I get there? Yeah, just jump here. So this is basically what we do, right? We built So you want to test DRAM, and we want to in the lab, right? Let me use the word he because I was working mostly on the GPU side of things. This is actually really like DRAM technology kind of thing, right? So he want to test many things in DRAM, including how fast can DRAM be, and can I open to put it in a higher level, like can I overclock the RAM to the point that it's go really fast? What's the effects on that with different temperature? And how do I test it? And in the meantime, we discover another security bug on DRAM that actually this is the first time in the world that this is discovered. It's called row hammer, where you can write a lot of things to DRAM and it will flip some neighbor's value. So basically, one thing you can do is you run a program normally, and you cause bit flips on someone else's program, right? And we actually show that this can happen. Then I think there was a patch from many companies, including like Apple, right? That patch for this bug that he discovered. But this is basically what he can do. He didn't buy a bunch of DRAM, right? Because he wanted to test the timing. And then the DRAM would be plugged to this thing, right? Over here, let me draw this. Oh, I can't edit, so let me use the laser pointer right here. This is an FPGA. Anyone, how many people know what's an FPGA? Anyone heard about this word, FPGA? Okay, don't, that's awesome, actually. It's actually, think about it as a programmable board where you can now program both the software and the hardware. Say, hey, CPU is too mainstream. I'm going to program my own hardware so that it run the software really quickly. So this is one of the things you can do to make your program run really fast. And we use it for many actual real application to make things faster. For example, yeah, it's kind of like handmade CPU, but for certain program. For example, there was a time, I think they might even do it now. Like if you are working in Wall Street, right? One of the things that you might be able to do is if you hear about the news, certain news, and you make a buy or sell decision faster than your friend. If you can make the decision faster than your friend, you benefit, right? You would make profit. You make more money. So some of these companies would basically buy FPGA so that they can make a decision really quickly. Basically, they run certain program on them and then make a decision whether you should buy certain stocks or not. You can use it to accelerate like machine learning application. These are another common things you can do, right? But what we use here is basically we use the FPGA to control DRAM because we don't want the CPU to control it because otherwise we cannot see anything we want to measure. Then you plug the DRAM that you buy, basically anything you can buy. A DRAM you can buy from the market, like go to Amazon.com and buy DRAM. And that's literally what we do. He bought DRAM from many manufacturer, right? And do the measurement. Put this on the FPGA. And then you can actually, well, to be honest, to be complete, right? We have the like this enclosing. Literally go to Home Depot. It's kind of like Home Pro in Thailand. And he bought the plexiglass glass, put this thing together, and put the heater inside it so he can control the temperature. And that's what we do as a PhD students. That basically we need to build a heat chamber that can control the temperature for your DRAM, right? And then the PC here is actually there to drive the FPGA and do the analysis afterward. And that's all, right? And you can see another PC right here. So he basically put in a bunch of DRAM, do the measurements, and then some of his research actually spawned from the measurement he found because some of them looks quite weird. Some of them looks quite weird. But to answer the original question that you asked, this is awesome. It's like, how do you measure this, right? You build tools to measure the timing. The other thing you can do, which is simpler. So this is an actual lab setting on a real DRAM, right? This is lab setting on a real DRAM. And you can then measure the limit of DRAM, like how hot it can be. How much can I overclock? Because these FPGA, literally what it does is also overclocking your DRAM beyond the control of your CPU. All right, so you can test a bunch of things in DRAM. So let me close the slides. The other thing you can do is, you can also, if you want to just not overclocking DRAM, go with the normal thing, right? Let me go to advice.com. Act as if I'm buying computer. All right, I'm basically literally searching for DRAM. See this? And do I have? No, here, memory. Okay, I cannot search DRAM. Interesting. Computer hardware, RAM for CC. Okay, I need to put the word RAM. Well, it's any website is fine, actually. Let's go with DDR5 here. All right. Oh wow, it's actually pretty expensive. I didn't know DDR5 is actually this expensive. I haven't bought one in a while. Well, I never bought DDR5 yet. Where's the spec? Where's spec? No, not ads. Okay, here you see this bus, 5,600 megahertz. You see that? Not sponsored by Advice. I'm not NIAM for sure. They did not pay me for this. Maybe I'm watching too many of NIAM videos and just use Advice by default. Sorry. But yeah, do you see the spec sheet here? What does megahertz measure? What does megahertz measure? It's a unit of what? Megahertz is the frequency, which is the inverse of the clock speed. It's a frequency. So it's a clock speed, to be honest, but you need to do the inverse to get the nanosecond, right? This is double data rate. So the actual clock would be 2,800. That's how DRAM works. Basically, you need to, because it sends the data on both clock edge. So in one clock cycle, you have data coming in on both clock edge. So the actual clock is 2,800. This is the speed for how fast your data transfer, but it's not the entire data. The entire data, you have to look at this. This is the clock, how many clock cycle is required to do certain operation in DRAM. So to read things in DRAM, you need to do certain operation on that. And this, you would multiply this by the clock speed because you would need, say, 36 cycle to read something. So you would then do 36 multiplied by 1 over 2,800. So that's how fast is a read to DRAM. In a more like, I don't overclock this at all. But you can kind of overclock this, like actually push the limit, right? That's how overclocking works, basically. All right, so I'm gonna close this and go back to here. All right, sorry, I go sidetrack a lot on how to measure these things. It is, and sorry if this is confusing you. I'm not gonna put anything here on the exam, right? How to measure this, the speed of your register or the speed of your RAM, right? But is the topic close to home? So I want to say what I know. All right, so now let's go back here. Let's go back here on our example. You have the two function call, right? Mount store and mount to, right? And here's the assembly code for the two functions, right? Do you see that in mount2, which is the function you call, you have a and b as an input, right? A and b as an input. you actually, if you look at the assembly code, you know that it assumes A is in RDI and B is in RSI. So you can just basically move A into RX is the return value, right? So it return it originally A and then you multiply by B. So eventually, because it's going to return A multiplied by B. It's going to eventually return A multiplied by B. And you see, right, first of all, after you call this function, the mount store just use RAX because it's no, right? It knows return result as in RAX. It just know, right? Because of the assumption that we have. All right. Because of the assumption that we have. Any questions? Any questions? All right, so that's how you manage function call when you pass the control and pass the data. Then, right, the last thing, local data, like when you have the variable in your function call, it needs the register, right? So let's say I have function one that are happily using, I don't know, RBX, RCX, and everything else. And then function two that function one call needs RBX. What should you do? What should you do here? I call some function that need register as well. And how many register do I have in total in x86? How many register in total am I having in x86 program? In x86 CPU, my bad. Actually 16, right? 16. Is that going to be enough for a big application? No, right? So what are some ideas that we have? What can we do? What can we do? Use the stack. Exactly, right? This is a stack-based language. C, for example, is a stack-based language where everything you do is in a stack discipline. So you can push those things onto the stack so that when you finish your function call, you return and anything you save is now on the stack, right? So when you call a function, you allocate things on the stack to, if you will, right? Basically, you would put whatever you need to save on the stack, and then you call the function. So what are the things you need to save? Register that you know that someone else are going to use. The program counter, right? The program counter. And once you do that, you can call the function and you can feel safe that no one is going to touch my data. And once the function call is done, I can then pop, right? And now I have all the data back. And that's how many of the language would be basically manage your function call in a stack discipline. So here's a call chain. For example, let's say I have a call chain of function called you calling who am I, like to the right here, right? And the function you call who call mi twice, and mi call mi once, right? So mi is recursive. The way the stack chain works is like this, right? Every time you have a function call, think of it as there's a whole frame on the stack that are related to that particular function. Right? When you need to call a function, you need to set up anything you need to save, put it there, make sure it's safe, then push the program counter, right, by the call instruction. And then when you are about to finish the function call, you have the finishing up code to make sure that if you save something, you recover it back before you return. or you return and you do the finish up by the caller. That depends on whatever assumption, who should do what. And the who should do what depends on how you want to program it and depend on the compiler. Sometimes you want this to be done by the caller. Somehow you want this to be done by the callee. All right. But the key concepts stand. The key concepts stand, right? You would put whatever you want. This data you need to save, put it on the stack frame. And then when you call a new function, you then push again, right? Now, there's one special register that are being used here that you haven't seen before. It's there to make your life a little bit easier, It's called the base pointer. The base pointer store the old stack pointer. Why do we need that? This is so that you don't have to do pop until you're back at the original function. You can then move RBP into RSP, and then you would then be reverted back to the original function. Because sometimes you don't need to pop everything. So in many cases, your compiler would then use the base pointer, and when you finish the function call, you would then make sure that RSP, or the current stack pointer, go back to the base pointer. All right, so let's go with some example here. The who am I, where am I, right? So the function u call who, right? So when this get called, right, the stack pointer would basically now shift to make sure I have everything related to the function who in this block, right? This block is called the stack frame. Just a name. There's a name for this. It's a stack frame. Each frame is for each function. Each frame is for each function that you have when you run a program. All right. Then the function who call what? What's the next function is calling? MI, right? So you call the function MI, you update RBP to have the new RSP. And then you update the stack pointer, save everything you need to save in the new frame for this particular MI function, and you do it again, right? And you do it again. And now you might be wondering by this point, why do I have to save these things? Why do I need a stack frame? Why do you need a stack frame? Again, I'll repeat this because you only have 16 register, and not all the function call would be willing to share and use a different register. You have no way to do that. You have no way to communicate that, because when you have a function call, you have no guarantee that they're not going to use RBX, they're not going to use RCX, right? So if you need it, save it, put it on the stack. If you need the value after the function call, you can put this on the stack, right? And now you can do this, and once the function is done, you just basically pop and revert the status from the RBP and RSP until you are on the next who am I again, right? And then you're done. Okay. And that's it. That's actually how x86 manage function call. Generally, how to revert the value of RBP. Okay, great question. This, right, how you go back? You put it on the stack. So RBP is one of the things that you put it on the stack. So that you know what's the old RBP. So typically these are something that you put on the stack. All right. Does it answer your question? All right, awesome. So here's basically more of a detailed breakdown of what goes into a stack frame. See, RBP, RSP, so this is our frame. Typically, the organization is something like this. I would have the return address which is call Q, you push in the program counter, right? Then you push in the old RBP, so that basically is like John asked, right? How do you revert back to the old RBP? You push it there. Then you save anything you want to save, like all the register that you use, all the local variable, and everything you need into the stack right here. And then this is when we have the input for function call, right? So let's say you have a function call that have 8 inputs, the 7 and the 8th input you get put there. It get put there. So you can then pass in 8 variable, right? And that's it. That's it. That's all you have to know on how x86 manage function call. And when you have this assumption, you're basically good at calling the function, passing down different variable, going back to the old function call, right? Going back to the old function call. So let's take a quick break before we come back and go through the example. The example is actually pretty easy, right? It just do increment by certain value. Increment by certain value. You have pointer P and you increment by that value pointer plus val. All right, so let's take a 5 minutes break. And sorry, my cat again. Let's do a let's say a 7 minutes break. We'll resume at 3:14. All right. So let's take a quick break to freshen up and process whatever we have so far. And feel free to type in the questions on the chat. All right. Now my daughter's toy is being. Oh, in class 9 is actually the older version of x86. That's something I need to announce about in class 9, that the input arguments, basically, if you go to here, slides here. For this, for your in class, this is going to be your first input. This is going to be your second input, and so on and so forth. It doesn't use this part. This is the older version of the assembly where you don't use the register. So that's for in class 9. All right. Yeah, it's all on the stack. It's all on the stack.
alternating. So this term and then 2 terms after that. So next term you cannot, but term after that you should take D soup data structures with D soup discrete. Yeah, just take it. Oh no. Oh, I remember this. This is the one you can shake it and it'll open. Yeah. 5. Yep. 4 is not enough. I don't want to learn. Your next term is going to be so easy though if you don't take 18. Why? I just need to get linear physics and calc 2 is going to be tough for me. Yes. I haven't done calc 1. I haven't done calc 1 in a while. You need basics of calc 1. I forgot everything calc 1 and I did calc 2. Just make sure you got your foundation. So much. Even if it seems like simple. What foundation? I don't know. Linear. Like foundation. Like matrix. Matrix. Like the first 4 weeks. All. Yeah, make sure you focus in the first 4 weeks, so you need that for the rest of the course. Yeah. Got it. And another determine. Yeah, that's what I did. I read it so hard. I've been cramming so many exercises this week. Professor Leonard. Calc 2, you listen the first 7 weeks. Listen to how he teaches. Oh, fuck, you're doing it, Chinda. You're dead, I have one. I don't remember the. I remember the. Unless my not fine. Like, hello. So, what do you mean, yourself?
All right. What? I think I'm muted. Oh, but I didn't hear anything. Okay, so let's resume the lecture with the example. Hopefully we have enough time to cover memory hierarchy, but we'll see. So this function is pretty simple. You have input pointer here, a pointer to long, right? And then another value come in, number. You do long y equals x plus val. X is the value that the pointer is pointing to. Then you do star p equals y. Then you return x. It's kind of funny in the sense that what it does really is increment your value, right? But then you would need to do these things in order to make sure the assembly, like when you compile, it becomes this one particular code, right? So what it does is, again, RIX is the return value, that's X, right? So you move RDI, this is star P. You put the value of star P into X, then you add, this is X, right? This is X, this is val. And you add val to X, and then you move ISI, which is Y, right, into RDI. This is star P. This star P, right? So P will still point. P would point to the updated data. P points to the updated data, but you return the old data. You will return, right, the old value, but P point to new value. For example, let's say I have star p equals 10, val is 15. This function would return 10, but star p would be updated to 15. So that's what it's doing. You update the pointer value to the new value, you add val to that, but you still return the old value. Any questions so far before we go to what happened if I call this function? Any question? So let's say I need to call this function, right? The function is what it does is originally I have 15 to 13. 15 to 13, and I call increment. I call the increment function that I have earlier. This is basically star p. This is val, right? A quick note, 15 to 13 is a class at CMU. It's actually a class almost equivalent to the next class for this. So the material that would be taught are like some of the lab, like assignment 4 is part of the material being taught in this class. But the lab would also include like implement malloc or implement a proxy server or optimize your code. It's a fun class, right? And for historical reason, there's also the same class. So 15 is the code for CS department. But for me, for example, I was electrical and computer engineering. So from the engineering department, we can also take this same class, but the code for the class is 18 to 13. So literally the same class. Sounds like plain class. There's so many other plain class in CS department actually, like OS or architecture or compiler or you just list all the topics that I actually like. I mean, actually, most advanced class can be a pain, right? But you learn through pain, and you also become expert through pain. I feel like that sounds really bad. Does it sound bad? Yeah, I think that sounds bad. So I'm gonna stop saying. I'll stop saying that. Okay, so what does it do? The first thing we do. What is this? What is this line? What is RSP? What is RSP? One pain, more success. We should not think about that actually. We can have fun when we learn new things, but the process of learning new things sometimes also involve grunt work. I would call pain grunt work actually. It's like you have to power through that. And once you learn it, it's actually less and less grunt work. So it's originally hard work that will become easier and easier and easier and easier. I personally, I hate the phrase "no pain, no gain" because I mean you can have fun and also gain something, right? So I feel like people who think that the only way to learn is to go with no pain, no gain, that's dumb. That's really dumb. All right. Computer science is still computer science. And we do get paid quite a lot as well. So that's another good thing with our career, right? Well, not me. I'm being a professor is really not paying well. Like my starting salary is so bad. But you guys, when you become the programmer and developers, you get paid quite well. So that's another thing we can enjoy, right? Um SysQ. Actually, that's part of the joke with the SysQ name. And the other part of the joke is SysQ it's like almost a wordplay with sick kill, which is when you go and send a signal to kill a program or terminate a program. All right, so before that, what is RSP? What is RSP? Sorry. Here, what is RSP? I need my pen. What's RSP? Today's class is so chaotic. Stack pointer, yes. Sorry, it's like my cat is behind me. Like jumping around actively. And now she's looking at me. I don't want to look back. The stack pointer. So why do we subtract that? Why do we subtract the stack pointer? So that we can set up for the next frame, So this is basically more in line with your in-class exercise. You put 15 to 13 into RSP plus 8. You put 15 to 13 here. What's 15 to 13? It's a constant, right, used by V1. It's a constant integer used by V1. So this is basically the local data, right? If you look at this, V1 is the local data. So you can put 15 to 13 on the stack. Then what do? What's the next thing you do? So you put 15 to 13 on the stack right here, right? What's the input? What's the input for the function I'm calling? There are two inputs, right? 3000 and V1, right? So where do we put the first input? V1. Okay, I'm gonna move to the next page, right? RDI would take the first input, RSI would take the second input. See, I put 3000 into the second input inside ESI. ESI is the shorter form of the RSI. Basically, I put 3000 in there. The next thing is, this is an address. This is RSP plus 8. This is basically ampersand V1. Ampersand V1, right? Because that is the same location where I store 15 to 13. So that's my first input. ESI now has 3000, which is the second input. RDI has address of V1, which is RDI. That's in RDI. That's the first input. That's the address of 15 to 13. All right. A quick note, right? You have move L, right? You use ESI, but move L is move only for 4 bytes. So it will zero out the higher 4 bytes. Basically, it's fine. You just put 3000 into RSI, right? That's a quick note. That's why. And the reason why you use move L instead of move Q, it makes instruction a little bit shorter. It makes the instruction a little bit shorter. You don't need to specify so many bytes in your instruction, so your code will be smaller. Second note, you see LEAQ. What is that? Anyone remember what's this instruction? LEAQ is used to compute the address. So you have 8 RSP, right? This is 8 plus the base, which is RSP. So now your address is 8 plus RSP. All right. So LEAQ is literally used to compute the address in this case, right? Not some optimization, not some fancy optimization done by the compiler. Now you have the inputs, percent %v1 and 3000, right? Now we call increment. So what happened? What would happen to the stack pointer? So two things. Let's say I call increment, and this is basically magic that happened. Increment do what, right? Increment update the pointer, to add val to it and then return the old value. So if you see the status here, you see that now it changed from 15 to 13. You add 3,000 to that, right? This is my percent %v1. Percent %v1 is now updated by 3,000. And then the return value would be 15 to 13. So that's what happened when you finish, right? When you finish. And then over here, you return v1 plus v2. You return v1 plus v2. This is v2. This is v1. You add them together. You add them together, right? And then when you're done, you add 16 to RSP so that RSP jump from here to here. So now you add the return address so that you can go back to the original function that called this whatever function. Right, and now the final stack structure is done. So that's it. That's the example here for our code that would perform a function call, prepare the stack pointer, and then return after we done everything, it returned back to whatever function called this call incr function. So that's a quick summary for what happened when you have a function call, right? And how do you build the arguments? How do you maintain the local variable, right? So in the case we have, that's our v1 and v2, right? And how do we maintain everything here, despite the fact that many functions can call this function? All right, so now we're gonna move to the next topic after assembly. So we're done with assembly. Any question about assembly? Any question about assembly? By the way, I'm gonna try to upload this video around 5 p.m. Should be at about the time that WebEx finish processing. So the example we have earlier might look confusing. Feel free to check the recording. And then if it's still confusing, let's use the Discord session for this, and also the review session also, to make sure it's not as confusing as you think. Everything is systematic. Everything is designed to do its own task, and that's all. So everything has its own rule, and that's it. You just follow the rule and then go to the next function call. All right. Now, I'll start to talk about the next set of topic. This is the last set of topic for this semester. We are almost done. All right, we are almost done. Now let's talk main memory. So today I'm not going to go through a lot of detail. I'm gonna motivate you why and what is memory hierarchy and why do we need one. So now let's talk the main memory. We've been doing many things in the main memory, right? The program are there, the data are there, stack and heap are there. So let's dive into this. Let's dive into this. The first thing I want to ask you is, if you need to buy RAM, what do you want from it? Let's say I can give you a magical RAM. What would be your desire that you want out of the memory? That might be too much. Free sneakers? Not sure if that's compatible. I guess yes, if I can. A lot of memory, right? I want my RAM to be as big as I want. Maybe 5 terabytes, 20 terabytes, right? Magic DRAM. What else? What else? How about the speed? How about speed? Price, right? It should cost 0 baht. It should be free, right? Magically, cost should go down. The speed should be really fast. 0 latency. Latency is the time it takes to do a certain thing. 0 latency means that if I need my data, it's available right away. It's magic. Unlimited capacity. 0 cost, right? What else? How about bandwidth? How about bandwidth? I want a lot of bandwidth too. I want to be able to do a lot of parallel access, right? If I'm running 10 different programs and they want to go to DRAM, they should all go to DRAM and they should be able to access their memory at the same time. But if you look at this, right? Compatibility. So compatibility is a great thing, but it's already supported. So if you plug DRAM in, it would work. Right? It would work because the hardware that control DRAM is designed to work with the CPU. These are what we call microarchitecture. Microarchitecture are optimization done in the hardware where it will work without any programmer support. Like you just plug in and it works. And then the ISA, right? As we learned earlier, the ISA basically would be the command that would enable all the things that we have, right? So oh, you're talking about compatibly in a sense that I buy DDR5, it would plug into the main board that only support DDR3. Like common interface, common number of pins. Is that what you meant? Oh yeah, then that's a really desirable goal, right? Every generation of DRAM should have the same interface, but that's really hard, right? Everything we just list is also really hard to support. If we have a large memory, it's likely to take longer to access, right? Because, I mean, imagine go to get your data, like when you have an address, right? When you have an address. So let me ask you this. How much time is this gonna take you if I give you an address and then I ask you to go to this location that are in Bangkok? Versus I give you an address that I told you this location is in Mahidol University Puttamonthon campus. Which one is going to be easier to find? The one that I basically tell you is within Mahidol University campus, or I tell you it's somewhere in Bangkok. Which one is easier to find? Assuming that you all have the same mode of transportation, by the way. The one that within Mahidol is gonna be easier, right? Because you know it's like the area is not as big as the entire Bangkok metro area, right? That's one thing. If I have a large memory, it's gonna take longer to get to your data. A fast memory also is gonna be expensive, right? Just look at the 5 DRAM that I showed you earlier. It costs like 10,000 baht, right? That's like almost half of my salary. It's so expensive, right? And parallel access is also expensive. You want bandwidth. Those things cost money, right? Having more bandwidth also basically it means that you need to build a DRAM that has a lot of pins, and also the internal circuitry is gonna have to support a lot more parallel access that have to be done at the same time. This thing costs money. They need transistors, so it costs money. It's not free, right? But also the other thing, if you look at it from the programmer point of view, right? How many people suffer from segfault and malloc so far? How is it? How is lab assignment 3? Oh, you can see. Okay. Sorry. So I use segfault personally. Then let me ask you this, right? Let's say I don't enable memory protection. So segfault is a way to protect the memory because you're trying to read or write to somewhere you don't belong to, right? So let's say I take it out and you run your program that's supposed to segfault, you modify someone else's data and your computer crash. Is that worse? How would you feel? Did you just elevate the nightmare from segfault nightmare to my computer crash all the time when I have bugs nightmare? Oh, broken. Come on. It's once you get used to the things that would cause segfault, trust me, it's gonna get easier and easier. But these are memory protection, right? And these are something that is a features that protect other program from your program that's about to destroy everything else running on your computer, right? So if you need a better way to debug, if you haven't tried GDB, try GDB. If you try GDB, check with me. There are tricks you can do in GDB to make your life a lot easier. All right, but if you look at it, this is going to be the last things we talk about in this semester. Virtual memory. How many people heard about the word virtual memory? No, not VRAM. Yes and no. It depends on how you consider that. Like consider VRAM, to be honest. But virtual memory as you know it, right? Because I want to use the word virtual as in like the abstract meaning of it. But the virtual memory as we know it is everything has an address, right? Everything you do has an address. Yeah, so one of the thing that virtual memory enable is it allow you to use the storage as a memory as well. So that's when your program use a lot of data. It is spit off into the storage area because you ran out of memory. How many people have a computer that occasionally run out of memory? What happened when what would happen to the computer when it runs out of memory? What would happen? Your computer would freeze, right? Typically it would get really slow, right? It would get really slow. So if it cannot install the app, that's when you run out of hard drive, when you run out of storage. But when you run out of memory, it would basically complain, not complaining, it just go really slowly. Why? Because whenever you need the data, it's not going to the memory anymore. Sometimes you go to the storage, and that's from nanosecond, you're looking at millisecond. So things are going to be 10,000 times slower, right? It's not actually crashing. It would just go at the pace of a turtle. Like it's going to be really, really slow. Uh, the other OS you can also configure the part that's we call this swap space, right? The swap. These are the reason why we call this swap is you swap a block of data from your RAM into the memory. That's why it's called a swap region because you swap your data into that place. But how about this? Let's imagine, right? Another thing about virtual memory is it enable things like segfault, which is a good thing because let's imagine that you can allow two program to run at the same time, right? And you do malloc and free. And imagine if you have to manage where you malloc and where you free. And you have to imagine you have to be careful about the other program's locations. That would be a nightmare, right? So the system gives you this virtual memory because every single address you see in C, in Python, in Rust, well, Rust doesn't give you an address, but every time you access the data, right? In Rust, in Java, everything, these addresses are virtual memory. These addresses are actually virtual memory. This is actually not the physical location inside your RAM, right? But we'll go through this and we'll actually show you why, and also for what purposes. Again, today I just want to motivate why you need to learn these things. So the OS and the hardware would work together to give us this illusion, and we'll work together to give you segfault when you do something dangerous on your machine, right? Inside the hardware, keep this particular image in mind. Your DRAM is a physical thing. It has certain address. It has a certain location to store the electrical charge, but somehow your program can find that, right? And here are some current memory technologies that you use a lot. When you buy a computer, you have the SRAM. These are really fast memory. It's actually consists of 6 transistors. And in the RAM that you buy, these are DRAM. This is 1 transistor and 1 capacitor. So which one is going to be cheaper? So let me just look at this number. How many people think then, I guess, DRAM is going to be cheaper than SRAM? The thing is, SRAM is actually going to be more expensive than DRAM. DRAM is cheaper, right? How many people heard of the word cache? When you buy a laptop, when you buy a CPU, it would tell you how big is the cache. Anyone heard about this word before? Cache. Yes, no? Clear the cache, right? You can also clear the cache. But if you buy a CPU, it would tell you, okay, on mobile, that also matters. The concept of caching is used everywhere, not just in the hardware, but in like database system or web application, right? Do you know that when you go access a website, the website's data is cached on your computer? It's actually being stored on your hard drive so that the next time you go to the website, it's actually can get there really quickly. Data center also do that. If there's a lot of popular data that Thai people are accessing, data center would put that data close to Thailand so that when Thai people access the data, it's readily available in the data center close by, right? Can someone give me the website that you can buy computer parts? Otherwise, I'm gonna go back to advice.com. Again, not paid. Okay. All right. Newegg. Chip? Okay, yeah, sure. I can do chip too. Chip online. JIB. Oh, it's called JIB. I didn't know. I guess always call it chip. CPU, right? Let's buy CPU. Okay, I guess I can also try Shopee. I'm pretty sure it's there. All right. Not, I don't want air cooler. I want the CPU. I guess I'll search i9. Oh my God. Here. All right. See this? This incomplete information to your CPU. It tells you the size of the cache, right? Okay, let me just do this. Spec sheet, go to Intel, like Intel website, who have all the information for us for sure. I just go look at a random CPU. It tells you number of cores, it tells you number of threads. Anyone know what turbo frequency mean? This? Anyone heard about this turbo boost technology? It's actually a really, really old technology. Yes. So your CPU actually would work at the higher clock speed, right? So the turbo boost, what it does is actually, let's say you run something that only need 1 CPU, right? In that case, what Intel chip and many other CPU actually from other brands would do is you can then overclock that CPU to make it faster, right? And this actually is done automatically. Cache. Only one. Interesting. Doesn't say different level of the cache and how much. Okay, this sucks. I thought I would have more detail. Yeah, typically there's multiple level of caching, right? There's no just one level, 16 megabytes, right? But these are the cache. These are small memory that's put on your CPU. These are a lot faster, and cache use SRAM. The RAM that you buy are DRAM, right? So now you might have a question where you say, hey, but what do they really do? If you need to store the data, the only two things, well, I guess three things that you really have to do is store the value, like trap the value inside the cell. Cell is where you store the electron. So you need to trap that, and then you can read and write to it. You can then read and write to the cell, and that's all, right? That's all. So you might have a question: are there other technologies? Yes, we will not talk about it today. If you're curious, let me know. There's many other new technology that come out that looks exciting. There's also new DRAM technology where you can put DRAM on top of each other. If you buy current GPU, they will do that. It's called 3D stack DRAM, right? So these are many things that you can use to make your computer fast. But again, SRAM is 6 transistor. 4 of them are used to trap the electron. The other 2 is used to read and write from it. For DRAM, 1 transistor, 1 capacitor, and as the name suggests, capacitor store the data, and the other transistor is used to access the data, right? And then I'll skim through this because we're almost done today. Again, the trade-off, SRAM is really fast, typically within like less than 5 nanoseconds, while DRAM is going to be less expensive. It's really cheap, but it's going to be slower. So if you look, these numbers are up to DDR4. I need to double check for DDR5. But for DDR4 and DDR3, you're looking at maybe it's a 12 to 15 nanosecond, right? Again, what about the upcoming stuff? This is already out there, right? Recent GPUs can do tiling, basically put a lot of DRAM next to each other. They can also stack them on top of each other. These are already on the shelf. Already on the shelf. I'm sorry for not updating the slides. A few years ago, these are not on the shelf. You can also have terabytes of memory using a totally different technology, right? Or you can do a hybrid of that. There's quite a lot of research. You want to have some summer projects, let me know because I have research in these directions as well, right? But the key point here is memory is slow. Memory is slow. And even with the new technology, is still slow. It is still slow. So when you need to write a fast program like the new cool API and libraries and all the tools, right? The programmer need to know how caching works so you can hide the slow memory access. So that's always one of the things that they would do. And you can definitely ask Ajahn Kana. Ajahn Kana is really good at making the program really fast. And he can tell you that if you compare the cache access to memory access, it's going to be a lot faster if your data is in a cache, right? The size of the data also can make optimization hard because when you look at modern program use a lot of data. It can be gigabytes of data. It can be terabytes of data. For example, if you look at DNA sequencing, it can be hundreds of gigabytes or terabytes of data, right? But you need to process all those, right? So you want to be able to speed up your data access, which means you need to speed up memory access, right? So we'll stop here. We'll stop here today. And before we leave, we have the between the class exercise. Assignment 4 is already out this morning. And do the in class before the next class begin. I have it due next week. When is next week? It is 30th, so I think it's July the 6th. So do it before July the 6th. If you have any questions, put it on Discord or email me. That typically are the two methods to reach out to me. All right. So that's it for the class today. Thank you so much. Any questions about the class and the material we covered today?